Solving complex numbers. Here's a funny cartoon that represents the imaginary number. Haha, so funny. Ways to remember. You can look up Complex Numbers Rap by Anna Plazafamilia on YouTube, as well as other cartoons and the imaginary number chart. The student will perform operations on complex numbers, express the results in simplest form using the patterns of the powers of I, and identify field properties that are valid for the complex numbers. To understand how to solve complex numbers, you must know the following definitions. Complex numbers. A complex number is a combination of a real number and an imaginary number. Imaginary numbers, or known as I. An imaginary number, when squared, gives a negative result. Radicals. An expression that has a square root, cube root, etc. And factor tree, a tool that breaks down any number into its prime factors. The easiest way to help you remember how to solve complex number radicals is to use the factor tree. Some complex problems will not use the factor tree, which is shown in examples 1, 2, and 3. Students need additional practice performing operations on complex numbers involving radicals. Example 1. What number is equivalent to the square root of negative 11 times the square root of negative 44? First and foremost, we need to get rid of the negative signs under the square root. By doing that, you take the negative and cross it out and change it into an I outside of the square root. Next, we have to use a factor tree, if needed, to find the prime factors of each number. Since 11 can't be reduced anymore, it's already a prime factor. However, for 44, it can be reduced to 11 times 4. Then, 4 can be furthermore reduced into 2 times 2. Once done with that, add up the i's and make it I squared and put all the prime factors that are left under one square root, like 11 times 11 times 2 times 2. Next, you group the numbers how many pairs. So there's 2 11s equals 1 11 on the outside, and 2 2s equals one group of 2 on the outside. So what you're left with is 11 times 2 times I squared. And since I squared equals negative 1, you can furthermore now multiply them all together. So 11 times 2 times negative 1 equals negative 22. Example number 2. The square root of 18 times the square root of negative 50. Like last time, we get rid of the negative and put an I on the outside of the square root. Next, we use the factor tree to factor out the numbers under the square root. So 18, you can factor out 6 and 3, and furthermore, you can also factor out 6 and put 2 and 3. Those are the prime factors now. For 50, you can factor out 25 and 2, and for 25, you can factor out one more time and make it 5 and 5. Once that's done, you gather all the prime factors and put it all under one square root. So 2 times 2 times 3 times 3 times 5 times 5. Once that's done, you pair them up and put them all outside the square root. So it's going to cancel out the square root completely. So now you're left with 2 times 3 times 5 times I. You multiply them all together, it will equal 30 times I, and then you multiply those two together and it will equal 30i. Example number 3. The square root of negative 27 times the square root of negative 32. Since we're familiar with these problems now, we now know to get rid of the negatives under the square root and change them into i's. Now we factor out 27 and 32. 9 and 3 can be factored out from 27, and furthermore 9 can be factored out even more to equal 3 and 3. For 32, 8 and 4 can be factored out, and both numbers can be both factored down even more. For 8, it can be factored down to 4 and 2, and 4 can be factored out to 2 and 2. For 4 over here, it can also be factored down for 2 and 2. Now, you add both the i's together and add all and put all the numbers or prime factors under the square root. So it would be I squared 3 times 3 times 3 times 2 times 2 times 2 times 2 times 2. Since the power of the square root is 2, you only group two numbers to equal one pair on the outside. So you group the 2 3's, and which would equal 1 3 on the outside, 2 2's, which equaled 1 2 on the outside, another group of 2, which equals 2 on the outside, and now you have left over a 3 and a 2. So now, once that's done, you can take I squared and make it -1, and times all these numbers on the outside together, which will equal -12. And under the square root, you can times 3 times 2, which equals 6. So now the final answer is -12 over the square root of 6. Real-world application problem example. Circuit components such as resistors, inductors, and capacitors all oppose the flow of current. This opposition is called resistance, or resistors and reactance for inductors and capacitors. All of these quantities are measured in ohms. The table shows the relationship between a component's resistance or reactance and its contribution to impedance. A series is also shown with the resistance or reactance for each component's labeled. The impedance for a series circuit is the sum of the impedance for individual components. Find the impedance of the circuit shown above. So what you want to do first is highlight the words to help you figure out what you're solving. So you're using the sum of the impedance for the individual components to find the impedance of the circuit shown above. So look at the chart and the picture to find the impedance number you need for the equation. So for the resistance, you plug in 5 to where R is, and then you look down and find what the impedance. So it doesn't change, the R doesn't change, so the impedance will be 5. Next, you look at the next section and you're finding the inductor. The inductor says 3, however, there's an I attached to the L. So you're going to put plus 3I. Lastly, you'll look at the capacitor and shown on the picture, and the number is 4. So if it's 4 here, there's a negative and an I, so you'll have plus -4I. Now, what you'll do next is just simplify. So if you add 3I plus or -4I, you'll get -I. And all you have to do now is bring down the 5, and that's your answer. So 5 minus I equals the impedance circuit. Problem is a high-level assessment question. This problem will be more difficult than the others, however, the same principles do apply. So first we get rid of the negative under each square root, and we put I on the outside. Next, we see if any of the numbers under the square root need to be factored out, which there is. However, 11 does not need to be because it can't be factored out anymore. 18 can be factored out with 6 and 3, and 6 can be factored out with 2 and 3. 50 can be factored out with 25 and 2, and 25 can be furthermore factored to 5 and 5. And 44 can be factored out with 11 and 4, and 4 can be furthermore factored out with 2 and 2. Now we group all of the i's together and all the prime factors and put that under the square root. So it'll be I3 with under the square root with 2 times 2 times 2 times 2 times 3 times 3 times 5 times 5 times 11 times 11, all under the square root. Now since the power of the square root is 2, we'll group all the numbers by 2. So it will end up being a group of 2, another group of 2, a group of 3, a group of 5, and a group of 11. Now with the I3, if using the number chart, the imaginary number chart equals -1, negative I. So once you change that to negative I, you can now multiply them all together. So 5 times 11 times 2 times 2 times 3 equals 660. And if you multiply 660 by negative I, the answer will be negative 660. Some last minute reminders. When you have an imaginary number squared, it will always come out to a -1. Also, the imaginary unit I is defined as I equals square root of -1. If the power of I is greater than 2, use the imaginary number chart to help you out.